welcome back. So, before the break, we were talking about the Kleene paradox, and as I mentioned, the paradox emanated from a relativistic bombardment of electrons on a potential barrier. We were given a potential barrier V0 and an incident beam of electrons was focused on that potential barrier, and we examined the various parameters, that is the transmission and refracted probabilities. So, the wave equation, let us look at the two regions that are involved. The first region is the region where the incident beam is flowing through or passing through, and the second region, region 2, is the region where the transmitted beam flows after interaction with the potential barrier. So, the wave equation across the two regions is given by the expression, that is psi 1 and psi 1 in region 1 and psi 2 in region 2. Now, to make physical sense, the wave function psi 1 and psi 2 need to be continuous across the boundary or across the potential wall, and not only that, their first derivatives also need to be continuous. Now, when we impose these two conditions, the continuity of the wave function and the continuity of their first derivatives, we obtain expressions for the transmission coefficient and the reflection coefficient. I am sorry, the transmission coefficient and the reflection coefficient, which are given at the bottom of your slide. T and R. T represents the transmission coefficient, R represents the reflection coefficient. Now, let us examine the behavior of this transmission and reflection coefficients in various scenarios. Now, if the kinetic energy is bigger than V 0, that is the kinetic energy exceeds V 0, V 0 recall is the potential barrier. So, the kinetic energy of the incident beam of electrons exceeds the potential barrier, then we have both a transmitted wave and a reflected wave, because both P1 and P2 turn out to be real, and we have a partly transmitted wave and a partly reflected wave. That this is the situation when the kinetic energy of the incident beam is more than the potential barrier. When on the other hand, E minus m is less than V 0, when the kinetic energy is smaller than V 0, we get a reflected beam, and the transmission and transmitted beam gets exponentially damped. So, we have two situations. If the kinetic energy exceeds V 0, we have both transmission and reflection, and if the kinetic energy is less than V 0, of course, there is tunneling and there is exponential damping on the transmission side, and of course, we have reflection as well. But the interesting part is still to come. However, if V 0 minus 2 m is less than E minus m is less than V 0, then we have a similar situation as we had earlier. P2 becomes imaginary and we have a total reflection. P2 becomes imaginary, therefore, we have a total reflection. Remember, T1 and T2 are given by these two expressions. So, in this case, P2 becomes imaginary and we have total reflection. What happens if the kinetic energy is less than 2 m, is the potential bar is greater than 2 m and the energy in the range of this figure? This is the most interesting case when the potential bar or the potential barrier is greater than 2 m and the energy, the incident energy is in this range. This is the potential barrier, V 0 is greater than 2 m, and this is the energy, the energy of the incident beam, and in this case both P1 and P2 turn out to be real, and therefore, we have transmission as well as reflection, partly transmitted and partly reflected. But V 0 now let us look at what happens. Now, the potential barrier is of 2m or greater. Now, if the potential barrier is of 2m or greater and the incident energy is in this range, that means what? That means after interacting with the barrier, you have E minus m minus V 0, and this is going to be negative. E minus m minus V 0 is going to be negative. Why? Because V 0 is greater than 2 m. So, E minus m minus V 0 is going to be, there could be situations at least where this expression is negative, and notwithstanding that, we are having a non-vanishing probability of finding the electron post or after passing through the potential barrier. In other words, we are likely to find out, or we are likely to encounter electrons with negative kinetic energy. The probability of finding electrons with negative kinetic energy to the right side of the barrier is not 0. This was a very interesting result. This again needed a radical solution to lend credibility to the underlying quantum theory or quantum philosophy. The argument that was propounded to resolve this issue was again to give up the particle interpretation and to look at to provide for the creation of particle pairs at the due to the interaction with the barrier. Recall that V 0 is greater than 2 m. So, recall that V 0 is greater than 2 m. Therefore, when the particle interacts with the potential barrier, there is a possibility that due to the interaction a particle antiparticle could be created, and as a result of which we could have particles moving across the barrier with negative kinetic energies. So, that was again a proposed resolution of the Klein paradox due to proposed on the basis of the fact that the interaction with the potential barrier of 2 m enabled creation of particle antiparticle pairs, and it was this pair creation which accounted for the generation of particles with negative energy across the barrier. See, if you have a situation where you try to localize a particle or locate a particle within its Compton wavelength, let m be the mass of a particle, say an electron, and you want to localize the particle or you want to identify the particle, you want to locate the particle within a region of its Compton wavelength. In such a situation, Heisenberg's uncertainty principle creates havoc, in the sense that if delta x is of the order of 1 upon m, if delta x is of the order of 1 upon m, and that is the Compton wavelength, then the fluctuations in momentum will be of the order of m, and therefore, the fluctuations in energy will be of the order of m, and that implies that even Heisenberg's uncertainty principle acknowledges, because of the mass energy relationship, that if the energy variance is of the order of n, or the energy deviation is of the order of m, that m could well arise due to the creation or annihilation of particles which are involved in the experiment. Now, we come to the issue of relativistic measurements. Now, in the case of non-relativistic quantum mechanics, observables are represented by self-adjoint operators which are localized in time, which are functions of time, and therefore, they are localized in time. Therefore, such operators are global in the context of coordinates or positions, but are localized in terms of time. However, what happens when we move towards a relativistic framework? In the relativistic framework, as you know, the fundamental postulate of special relativity is an upper bound to the speed of propagation to the speed of light, and therefore no signal. Because no signal can propagate with more than the speed of light, therefore measurements have to be localized now, both in terms of time and space. In other words, relativistic operators or measurement operators must be localized both in space and time. And as a corollary to this, what happens? The causality requirement says that if two points in space time are connected by a space like interval, then in other words, if they are causally disconnected, then their operators cannot influence each other, their measurements cannot influence each other, and because their measurements cannot influence each other, the corresponding operators must necessarily commute. But let us see what happens there if we retain the single particle case. Let us consider a localized particle or a localized wave function as a delta wave localized at the position x equal to 0. We represent it by delta of x. The initial wave function at time t equal to 0 is localized at the origin at x. Now, we evolve this wave function using the Hamiltonian under root minus del square plus m square. You recall that this is the relativistic Hamiltonian arising from or emanating from the mass shell condition. E square is equal to p square plus m square. You replace them with the respective operators, you get the Hamiltonian, and this Hamiltonian for the relativistic Klein-Gordon equation. The wave function solution of the corresponding wave equation can be written as psi of t x is equal to exponential minus I t into delta x. Remember, delta x is the initial wave function. Converting delta x, the whole expression into Fourier space, what we get is the expression that is given right at the bottom of your slide. Now, this equation can be solved exactly. First of all, you integrate over the angular variables, and by integrating over the angular variables, you get the expression on this slide. And then you do complex contour integration, and after doing complex contour integration, what you find is that for any t greater than 0, at any t greater than 0, you find psi t x unequal to 0 for any x. Now, this result is very fundamental. What does it say? It says howsoever small t may be, so long as it is positive. That means, starting at t equal to 0, even for infinitesimal evolution in terms of time, the wave function completely spreads and across all space, all coordinate space, and the value of the finding the particle, the probability of finding the particle at any point in space is not 0. So, this again violates causality, because causality requires that propagation should be confined at most to the speed of light, which in this case is clearly violated. In other words, you can say that the probability moves or leaks out of the light cone by virtue of this result. So, these problems, all these problems enabled or required a radical rethinking of the quantum mechanical framework as it stood at that time, and it was not really possible, keeping in view such blatant inconsistencies, to be able to merge the fundamentals of quantum mechanics or particle based quantum mechanics with the special relativity. So, the outcome of all this was the origin of the concept of quantum field theory. Before we talk about the concept of quantum field theory, let us understand what a field is. Now, given a certain space, given any space, for example, the space in this room, you could allocate a particular variable to every point in this space. For example, the simplest example that comes to mind is the temperature. At every point in this three-dimensional space, you could allocate the temperature in terms of degrees centigrade or Fahrenheit or whatever, but that particular temperature would obviously depend on the point at which it is being worked out or calculated. So, naturally every point will have a different temperature, a different value of that expression. Similarly, now this is the case of a scalar field, where you are simply specifying a number, and by virtue of specifying that number you are giving a complete description of the physical variable, in this case the temperature. This is called a scalar field. The temperature field is a scalar field. You could also possibly assign a vector at every point in this particular room. Every point in this particular room, you assign a vector that has a magnitude and has a particular direction. That would be a vector field, for example, electromagnetic fields. So, this is an example on your slide of what a field represents. Every point on this screen is carrying a certain number, is allocated a certain number, and that is how we define a field. There is an underlying manifold. On this manifold, we assign every point on that manifold is assigned a number, and then we create functions out of those numbers which are assigned to every point on this space. So, there are really two layers in this case. In the case of quantum mechanics, classical mechanics or whatever, we just have one layer. We have a space time, and on that space time we define our variables of interest, like we have the trajectory in configuration space, or we have in this case in the case of quantum system we have a Hilbert space. So, there is just an underlying space and physical variables are defined over that space. In the case of fields, there is a two-tier structure really. You have the underlying space and underlying manifold, that can be Minkowski space, that can be Euclidean space, that can be whatever space you like, multidimensional space, or whatever space structure you want, a torus may be, but on that space you define a variable at every point on that space, and that constitutes our field. These will be the operators that these variables representing or that are defined on every point of our space time represent the operators which will later be quantized and so on in canonical quantization, and then we construct functions of these operators like the Lagrangian, Hamiltonian and so on. So, it is a two-tier structure in contrast to what we have in traditional dynamical systems, right. So, obviously, the field as it is, field constitutes of an infinite number of degrees of freedom, and it is quite natural that it will have infinite number of degrees of freedom. The Lagrangian is a functional of the field variable. No, here we come to the second tier. The expression that you see within the square brackets, this is the first tier. X t are the underlying space, are the variables in the underlying space, the manifold. Phi of x t, phi dot of x t, these are the field variables that are defined on every point of the underlying space. L of phi and phi dot is the function of these field variables. These field variables can be quantized, what is called normally called the second quantization. However, of course, we shall not be focusing much on second quantization. We shall be focusing more on the path integral approach, which is an alternative to quantization. So, or rather another different mode of quantization, you can say, an alternative to canonical quantization, but nevertheless quantization, but in a different approach. So, that is what a field is. So, as I mentioned, we have a two-tier structure here. You start with an underlying manifold M. The field function phi x of t is a mapping from M to omega. It maps every space time point to a function space phi x t in the space of functions omega. Omega is the space of functions, phi x t is the function which is mapping the underlying space to omega, and then Lagrangian and all those are functions of phi which are mappings from omega to r or c, as the case may be when you are talking about complex numbers. Now, let us try to understand how the quantization went about, or how the second quantization operated. If we look at look at quantum mechanics, what we have done so far, if we look at quantum mechanics as we have done so far, we can recover the quantum mechanics as a special case of quantum field theory. How is that? Let us have a look at it. The first expression, the expression in the red box, or the entire first equation, is the equation for the action in the case of a field theory. In this case, it's a scalar field theory. So, in this case, this is the action for a scalar field theory. If you look at the expression, this expression for a zero with zero spatial dimensions. Let me repeat. The first expression, the first equation is the expression for the action in the case of a scalar field, a regular scalar field, that is a Kleene-Gordon field. For a zero spatial dimension case, if you are looking at a zero spatial dimension case, then you end up with this particular expression, which is there in the green box. Now, if you compare this expression with the harmonic oscillator action, there is literally a one-to-one correspondence between phi and q. If you look carefully between the two green boxes, the green box representing the first equation and the first green box representing the zero spatial dimension field, and the other one representing the harmonic oscillator action, there is a clear cut one-to-one correspondence. Now, you recall that when we did quantization of the harmonic oscillator, we quantized which variable? We quantized q. So, the natural corollary is that if we are to quantize the variables in the context of QFT or quantum field theory, we would be quantizing the field variables phi. So, q corresponds to phi, and we quantized q when we talked about quantum mechanics, and therefore, we will quantize phi when we talk about quantum field theory. And our underlying say Minkowski space or other Euclidean space variables will simply serve as indices for the identification of the fields at various points in the space, underlying space time. So, the important thing is, as I illustrated, quantum mechanics can be recovered as a special case of quantum field theory when we substitute, when we take the spatial dimensions to be 0. When we work in just the one time dimension, 0 spatial dimension, 0 plus 1 dimensional space, underlying space, then we recover the quantum mechanics as a special case of quantum field theory. That enables us to move or get a idea, a feel of what we should do to to quantize our field theory. Because we quantized the dynamic variables q, we shall now be quantizing their correspondents in quantum fields, and that is the field variables phi, right. So, in canonical quantization, what we do is we upgrade the dynamical variables as operators. We upgraded our q and p to operators, and so we will do the same prescription here. We will upgrade the field variables phi and the corresponding conjugate momenta pi as the dynamic variables of the theory. And moreover, there is one more point here that is given in red. The fundamental feature of special relativity is that space and time need to be placed on equal footing, and because QFT is a formalism that has been devised in order to combine together the quantum mechanics and field and special relativity, we shall be using our formalism as far as practicable shall be based on an equal identification or parity between the spatial and time variables. And that is in fact required for Lorentz invariance as a matter of fact. And the underlying space time of course will serve as the index for identifying the fields at various points. The matrix element which is given here, the time ordered operators phi x1, phi x2 in the ground state are usually called the 2-point Green functions or the correlation functions or the Feynman propagator. You call them so many almost synonymous names. They are basically the time ordered product of the respective number of operators in the ground state. We have similar expressions in the interaction states as well. In Euclidean space, this is the expression that we shall of course, we shall be working it out, but this is the expression for the 2-point function that we end up with. In the now we talk about the 0-dimensional field theory. So, see, my scheme is that I will start with discussing the 0-dimensional field theory. 0-dimensional field theory I have selected because it gives you an overview, it gives you a feel of the various. First of all, it gives you a feel of the various terminology that are singular to quantum field theory. That is one point. The second is the methodologies, the approaches that will be followed to work out those particular terminology terms or to work out those particular quantities. That is the second step that that is relevant. And thirdly, another important point is that it without the complications arising from the structure of Minkowski space, by having 0-dimensional field theory, we are able to assimilate the fundamentals and then apply them gradually to the complex Minkowski space. So, let us start with 0-dimensional field theory. What is 0-dimensional field theory? In the case of 0-dimensional field theory, what is the underlying space time? The underlying space time is a point. If we look at a 0-dimensional manifold which is compact, then we have only one point in it. So, therefore, the quantum field can be described as the assignment of a number at that given point. Any real number, in the simplest case, a real number, the assignment of a random real number at our point, which corresponds to our space time, will define the field, will identify the field. So, in other words, our field is a mapping from the point to the set of real numbers. Secondly, Because we've got just one point, there is no metric and there is no definition of length, and therefore the terms that involve the length quantities are irrelevant, will not figure in the action, and the action will contain only the quadratic term in the variable. The other point is that the Lorentz group is trivial, and all its representations would be trivial. And second, the next point, because the Lorentz group is trivial, there will be no spin involved, and so these are the features. These are the features that define a zero dimensional field theory, and in the simplest case, as I mentioned, the field function is simply allocation or a relation between a point which acts as the underlying manifold and the space of real numbers. We will continue from here. Thank you.